1.7 Periodic Trends. So I recommend having your periodic table out so that way you can look at it. I also recommend having Coulomb's Law in front of you, just like a note to yourself, because that'll be useful for a lot of these. So, the point of this section is to know why the periodic trends exist. You could, of course, memorize all of them. Like, if it goes from left to right, it either is increasing or decreasing, or if you're going from top to bottom, is it increasing or decreasing? But the main focus is on why they exist in the first place, because the trends are just patterns. And so knowing the behind the scenes of why they exist is what matters in the section the most. And so you could see here in this why, we're usually talking about atomic radius, so we're talking about the distance between the nucleus and the valence electrons, and we're going to use Coulomb's law a lot. The trends that you have to know about are these four listed here. So electron affinity, electronegativity, ionization energy, and atomic radii in general. So let's start with atomic radii. So you could see here, we're going in this picture from the nucleus up to wherever that valence electron is. And so we use the Bohr model when representing this because it's a lot easier than thinking of the orbitals like SPDF, because that's a lot more complicated. So earlier I said Bohr's model is useful. Well, this is one of the examples of why it's useful. And so if we're going down the periodic table, the atomic radii is going to increase. So from H to Li to Na to K to Rb and so on. Great. And so that makes sense because we're talking about the energy levels or the shells. And if I think about Bohr's model, the first period here, so the H and the He, that would be represented by this first blue circle here. And then we have period 2, that would be the second one. And then period 3 would be the third. Period 4 would be the fourth, and so on. And so it makes sense that as I go down the PT, it's going to increase the atomic radii. Now, going across from left to right, we have to think about the radii and the charges involved. And so we need to think about Coulomb's law, which I have right here. And so, even though we're increasing the amount of stuff within the actual atom, so for example, I'm increasing the valence electrons added on the outside, I'm adding more protons in the middle, and so on, we have to think what effects are affected based off the atom. And so when I think about going from left to right, my proton number is increasing, so my Q value is increasing, and then my number of valence electrons are also increasing. So because I have more of the opposite attractions, they're going to attract more. And so my attractive force is going to increase a lot because, again, I'm increasing the protons and the electrons. And so the radii, or, the distance between the outside and the nucleus, is actually going to decrease going from left to right. A lot of students think the opposite, going from left to right, it's increasing because I'm increasing the amount of stuff you have. But by increasing the protons and electrons, again, you're making the attractive force more attractive to those protons and electrons, and so therefore that radii is going to get smaller going from left to right. So you have to be very careful about thinking on what's happening and how it affects via Coulomb's law, for example. Alrighty, electronegativity is another trend you need to know. Here I have a chart that shows you the electronegativity trends. So going from left to right, it's going to increase, and then going from bottom to top, it's going to increase. So first, what is this, in case you don't know? So it's attracting shared electrons in a covalent bond. So we haven't talked about covalent bonds that much other than like generically, hey, they're sharing electrons. We're going to focus on this in another unit later on with Lewis dots and all that stuff. And so if you don't remember that or didn't take Gen Chem, don't worry, we'll review that when we get there. So for now, just know that for the definition. And so the atom's nucleus is attracting these electrons from a different atom within a covalent bond. And I'll show you what I mean with an example in a second. So if I have a higher electronegativity value, I have a stronger pull on those electrons within that shared bond. This value is theoretical, so there is no like concrete experimental data that says this trend up here, but it's something just based off what we know and how, attraction works and all that stuff. So this value is not measured in any particular lab experiment or whatever. So when I'm thinking about Coulomb's law and I'm thinking about the radius, I have to think about what's happening as I go from left to right, for example. And so when I'm thinking from left to right, I have more protons in my atom. And so those protons in the atom can attract more electrons from a different atom compared to something that has less from left to right. Then if I think from top to bottom, I think about distance in terms of the radius. So if I have stuff down here, for example, it's not going to attract electrons from a different atom as much because there's so much radius to go through. So if I think about Bohr's model again, I have a whole bunch of energy levels, and so therefore there's just so much distance between that nucleus of one atom to the electrons of another atom. So we got to think about stuff like that. So the noble gases are the very last family over here on the PT. They don't want to share electrons if they don't have to. So in terms of the electronegativity trend, where I'm going from left to right, I am discluding them. So we do not want to think about the noble gases when sharing electrons. So they are not part of the trend. Make sure you know that. They have a full octet. They have full valence electrons. So in general, they don't want to share. Sharing is more for if you have space in your orbitals and you want to share electrons in order to, fill up your shells. So here's an example. We have nitrogen over here and oxygen over here. And so let's say we have some compound. The compound right now doesn't really matter. So we're just going to think about the electrons shared between the nitrogen and the oxygen. So if I think, for example, I have these two electrons being shared between nitrogen and oxygen. Let's say this electron here that I'm drawing on top of is from nitrogen, and this electron here is from oxygen. So these electrons are being shared within both of these. Now, oxygen has more protons, so this shared pair is going to go more towards the oxygen because oxygen has more protons. If I have more protons, think of Coulomb's law, I'm increasing that Q value, so that means I have a more attractive force between the electrons here versus the nitrogen to the electrons. So my attractive force is going to increase on that oxygen, and then it's going to decrease the distance between the electrons and this oxygen. So you need to use Coulomb's law in order to explain how this attraction works. So again, the nitrogen was sharing an electron with oxygen, so the nitrogen's electron is more attracted to oxygen compared to nitrogen. So be very careful about that kind of thing. Cool. Alrighty, so here's your turn. You're going to do it for ionization energy. And so here's the definition. It's removing an electron from the atom. We're usually talking about the valence electron. If I already removed the valence electrons, then I'm talking about whatever the next outermost electron you have. So if I had valence electrons on, let's say, the third period, for example, third energy level, I got rid of all those. So now I only have electrons in the second energy level, then those would be the next ones you remove. So it really depends on like where you are in terms of it. For now, we'll just think of just one. So without looking it up, try doing these two things. Try to justify using Coulomb's law and, atomic radius, and then I will show the answers in a few moments. So go ahead and pause this video. Alrighty, so here we go. Boop. And so I use Coulomb's law. I didn't write it in a sentence, so if you're confused on this, please ask. But otherwise, here's your answers, and I highlighted which one is which. There we go. Alrighty. So ionization energy, there's some other stuff you need to know. So let me move this. And so we have something called electron shielding. So the valence electrons, the outermost electrons, they sometimes get blocked attraction-wise from the nucleus to those valence electrons because of the core electron. So as a reminder, the core electrons are the electrons that are in the atom that are not the outermost one. So it's literally the rest of them. So for example, in this picture here, we have a second energy level, and we have the electrons here. And so you could see in this blue arrow, they're being attracted to the nucleus, but there's also the repulsion of the other electrons since they're both similarly charged. And so that's why there's a repulsion there versus the attraction between the positive nucleus and the negative outer electrons. So that's something you need to know just in general. And it can be related to ionization energy. And so one of the things that is very common to see on College Board is the distance from Coulomb's law, so this part over here, versus electron shielding. Most of the time for MCQs, especially with periodic trends, it tends to be about the distance / the atomic radius, but shielding could also be the answer. You want to think about what is going to potentially affect things more. Is it going to be the repulsion here or the attraction here? A lot of it is relative, honestly, so it's hard to like super duper distinguish, but in general, we're usually using Coulomb's law for the answer. Okay, in terms of other ionization energy stuff, so here's a chart to show different ionization energies. And so you might see a chart similar to this on the College Board exam. You are not required to memorize it. That's a waste of time. But you should realize what kind of information is given to you in this kind of chart. So the ionization energy, so this is the energy involved to, remove the outermost electron, as I said right here, energy to remove electron. And again, usually we're talking about valence first, and then we might be talking about more. And so here you could see ionization energy is kilojoules per mole. And so usually it's written that way. It's usually with joules, because joules is related to energy. Now, you can see, for example, sodium. Sodium's right here, number 11. And you can see the first, ionization energy. So that first electron, it's not going to take that much energy compared to the second. Now that makes sense. If we look at where sodium is, the valence electron here is going to be in 1, 2, 3. So 3s1 if I was using electron configuration. And so when I remove that one, I'm going to make it a nice stable atom because the orbitals that are filled will be 2p6 over here. So those are super filled. And as a reminder, when you have a filled, the filled orbitals in one of those orbital things in general, that's really good. So I filled all 3 of the p orbitals, and that's nice and solid. If I remove the next one, that's removing one of these 2p electrons in the orbital, and so that will make it not so filled anymore. So for example, the second one would make that sodium 2p5 instead of 2p6, and so that's not as stable, and so it takes a lot more energy to remove it. And then removing the next one would make it 2p4, and then removing the next one, and so on. And you could see it really is increasing a lot of energy involved to remove those electrons. You could see the 10th electron will take a drastically bigger approach in terms of removing electrons. You could see the same trend for magnesium. So magnesium is here, and so I have 3s2 in my filled orbitals, and so when I remove one, I'm still at 3s1. If I remove another one, it's still not so bad, and then it becomes super drastic because now you're going to remove stuff from the 2p6 area. And so that's how it makes sense for this chart. So make sure that you understand why there might be jumps in between how much energy. So here's like aluminum's jump, for example. Here's silicones and so on. Why those jumps exist. Another thing to know is writing those electron configurations. So, you heard me say it orally where I said sodium is at 3s1. Well, if I removed 1 because of ionization energy, then that's going to be no more 3s. It's just going to go up to 2p6 and then so on and so forth. So make sure you know that. That definitely could be an FRQ part where you removed, I don't know, like 3 electrons or something, and then now you have to give the correct electron configuration based off how many you removed and so on. So just make sure you could do that. For these periodic trends, there's always exceptions. Remember that trends are general. It's a general guideline of going from left to right, this exists, from up and down, this exists, but there will always, always, always be, things that don't follow the trend. And so you need to sometimes know why. Usually knowing why is based off previous knowledge. So like electron configuration, for example, is a really big reasoning on why some of these things exist. So here's ionization energy represented by a graph. And so you can see going from left to right, it's increasing H to He, Li through Ne. Again, it's just increasing. However, you can see I marked boron and oxygen. You can see it doesn't quite follow the trend. And you can also see here some other ones that are not quite following the trend either. But in general, it is increasing from left to right. So let's think about boron. So boron is over here. And so if I were to write down the electron configuration of boron real quick, and let's just do it the long way. So 1s2, 2s2, 2p1. And so ionization energy, we're trying to remove electrons. So I'm trying to remove this one over here. And so when I remove that, that's stable because the next fullest thing will have a full orbital. And so that makes sense that boron will use less energy compared to beryllium, because by removing the electron in the p orbital, it makes this super duper stable atom because this is a filled orbital. And then let's look at oxygen. So I'm going to write down the electron config for that. And then oxygen is 1, 2, 3, 4. And so I'm going to visually draw the orbital diagram, but only the 2p4 part because I'm too lazy to draw the rest. So 1, 2, 3, 4. Okay. And so remember, ionization energy is removing an electron. So I'm removing 4, becoming 3. And if I'm looking at this, I'll be removing this guy over here. So that's going to come off. And so now I have all of my, orbital shells filled up halfway. Being filled up halfway is very stable, and so it's less energy for this oxygen compared to nitrogen because I'm making this be all half filled. So knowing why things are half filled, very, very important. Yes. So as a reminder also, remember that electrons are repulsive. So because they're sharing this one orbital here, by removing one, that also helps alleviate that repulsion in that specific p orbital. So that's another reason why it's easy to remove that. So it's not only just filling them all halfway using Hund's rule, it's also, the repulsion. Okay, electron affinity. So electron affinity, as you can see the definition here, it's the energy to add electrons to an atom. So you're making a negative ion. As a reminder, a negative ion is an anion. Another definition, in case you want a different definition, is a neutral atom's likelihood to gain electrons using some kind of energy. So either way, you're adding electrons or you're gaining electrons, you're getting more electrons. And so one thing from Gen Chem, just for a quick review, you have endothermic. Endothermic is the system needing energy in order for something to happen. So whether that's a reaction or whether it's to gain electrons in general or something. So again, endothermic is gaining energy. And then exothermic is energy that is escaping the system. The way that I personally memorize this is endo sounds like enter, so you're entering either heat or energy or something, and then exo looks like exit, and so energy or heat or whatever is exiting the system. So that's how I remember. And so when I think about electron affinity, I'm thinking about attractions of valence electrons. Again, we're using Coulomb's law in order to think about this kind of thing. And so here is an example problem where you have a higher affinity, oxygen or fluorine. So think about the number of protons in oxygen versus fluorine, and then you'll see why one would be a better answer than the other. And so if you look at your PT, fluorine is more protons compared to oxygen. And so by having more protons, you're going to attract those electrons that you gain more likely anyway. One thing that I reviewed here for endo versus exo, one reason is because of when you're adding electrons to a neutral atom, so that would be the first electron affinity, energy is released, usually, when I'm adding an electron to a neutral atom. You need more energy to add another electron. So that would be the second electron affinity or the third electron affinity. That's when energy is needed. And so that would be endothermic. Usually. Cool. Okay, so type of questions are usually asked on the PT. It's always the why. It is almost always Coulomb's law or using the atomic radius in order to talk about it. And also, if you're going to use atomic radius and you need to explain what atomic radius is, make sure you talk about from the nucleus to the valence electrons of one atom. Or if I'm talking about, for example, electronegativity, so going back to that slide here, you need to talk about the electron from nitrogen being attracted to the nucleus of the oxygen. Be specific on what electrons you're talking about being attracted to what. Again, it depends on which trend you're talking about. So if it was an FRQ, for example, you want to make sure that you super explain who is being attracted to who. If you don't give that explanation, you might not get the point on the FRQ. So be very, very careful. Do not talk about the periodic table. So, for example, the trend for electronegativity from left to right, it is increasing. If you say that in an FRQ, where you say literally, on the periodic table going from left to right, it is increasing, you will not get the point. You have to explain why using the atoms themselves and not just the trend from memorizing the trend. You're always going to, or a lot of the time, not always, you're going to compare two different elements about a trend. So if you're given oxygen versus fluorine, and then you're given atomic radius, you need to explain which one's going to have a bigger atomic radius and why. This is both common for MCQs as well as FRQs. Again, Coulomb's law / atomic radius is going to be probably your best friends in these explanations. You want to focus on the structures, electrons, whose protons, whose nucleus are we talking about? Be specific. Again, explain why. You can obviously talk about electron shielding a little bit, but do not just focus on electron shielding. You want to talk about those attractions between protons, between electrons, and so on. Here are the trends to know that's summarized in, the thingies I printed out for you. You don't need the non-metallic or metallic character part. You could also draw these on your periodic table if you want to for your own reference. Just make sure that you know them for memorizing purposes. Or you can at least justify it. Again, you don't have to necessarily memorize it if you know and understand how Coulomb's law works. Cool. Alrighty. Bye.